All right, today we are popping the hood on an absolute legend in the world of AI, ResNet-18. We're not just going to talk about the theory, we're going to deconstruct the actual Python code piece by piece to really understand how a few simple, repeatable blocks can be stacked to create one of the most influential architectures ever. This is the code that literally changed the game. So let's dive right in.
So here's our game plan. First, we'll look at the problem ResNet was designed to solve. Then, we'll get into its secret weapon, the residual block. From there, we'll see how to assemble the full architecture, we'll follow the data on its wild ride from input to output, and finally, we'll look at the numbers to see just how big this model really is.
Okay, first things first, why do we even need ResNet? Well, back in the day, the mantra in deep learning was, deeper is always better. But researchers kept hitting this wall. It turned out, after a certain point, adding more and more layers actually made the networks perform worse. The learning signal, the gradient, would get weaker and weaker as it traveled backward through all those layers until it basically disappeared. That meant the earliest layers just couldn't learn anything. This, my friends, is the famous vanishing gradient problem.
So that was the big question on everyone's mind. How can we build these massive, super deep networks that don't just break themselves? How do we get them to actually learn better? The answer, it turns out, wasn't some crazy complex new type of layer. It was an idea that was almost deceptively simple.
And that brings us to the absolute heart and soul of ResNet, the residual block. You can think of this as the single Lego brick. If you can understand this one little component, I promise you, you'll understand the entire philosophy behind ResNet. The whole castle is built from this one brick.
The whole brilliant idea behind this block is something called a shortcut connection. Just imagine your data is traveling down a long road, and it's getting transformed and changed at every single stop. Well, the shortcut is like a pristine express lane. It lets a perfect, untouched copy of the original data completely skip a few of those stops and then meet up with the transformed version a little later. This is the key. It ensures that the original signal never gets lost, no matter how deep this network gets.
So let's put a formal definition on that. A residual block is just a small network unit with two distinct paths. You have the main path, which does all the heavy lifting, the convolutions that detect features and the activations that decide what's important. And then you have the shortcut path, which, well, it does almost nothing. It just carries the original input forward. The real magic happens when these two paths merge back together.
Now let's see what this looks like in terms of code logic. It is a super simple three-step recipe. Step 1, you take your input, let's call it X, and you immediately save a copy of it. We'll call that copy shortcut. Step 2, you send the original X down the main path to get processed by a couple of convolution layers. And step 3, you take the result from that main path and you just add the shortcut variable right back to it. That's it. That's the whole trick right there.
And believe it or not, this one single line of code is where all the ResNet magic happens. Layers.add, in parentheses, shortcut, X. That is the whole thing. This is the moment that express lane merges back onto the main highway. See, by adding the original input back, the network no longer has to learn the entire transformation from scratch. Instead, it only has to learn the residual, just the small change or the difference that the main path needed to apply. And it's way, way easier for a network to learn small adjustments than it is to learn a whole new function.
Okay, but there's a catch. What happens if the main path actually changes the shape of the data? Like, let's say it halves the image size and doubles the number of channels. Well, now you can't just add the original shortcut back, right? The dimensions don't match. The math just won't work. And that's where this second type of shortcut comes in. We call it a convolution shortcut. All it is a quick one-by-one convolution whose only job is to resize that original shortcut so it perfectly matches the new shape of the main path's output. Then, the addition can happen without a problem. Okay, so we've mastered our fundamental building block. We get it. Now let's zoom out and see how we actually stack these little guys together to build the entire ResNet-18 architecture. This is where that one simple idea really scales up into a deep, incredibly powerful network.
And when you look at the blueprint, it's just so elegant and systematic. The whole thing kicks off with one standard convolution layer to get a first look at the image. After that, it's just 4 stages. And each stage is made up of 2 of our residual blocks. And just look at the pattern in the filter counts. Stage 1 has 64. Stage 2 doubles it to 128. Then 256, and finally 512. It's just a simple, beautiful, repeatable pattern.
And remember that special convolution shortcut we just talked about? Well, this is exactly where it becomes essential. At the very beginning of stages 2, 3, and 4, the network cuts the image size in half. It downsamples. In the actual code, you do this by setting the stride parameter to 2 in that first block. And that's the signal, right? That's what tells us the dimensions are about to change, and it's the reason we also have to set conv shortcut to true, so that one-by-one convolution can resize our shortcut path and make sure all the math still lines up.
So we've built the network in our heads. Now let's switch hats. Let's follow a single image on its journey as it flows through this whole architecture we've designed, all the way from a humble grid of pixels to a final, confident prediction.
Let's trace this journey. We start with a 32 by 32 image with 3 color channels. The initial convolution layer turns it into a 32 by 32 tensor, but now with 64 channels or filters. See? Same size, but deeper. Stage 1 keeps that same shape. But now watch stage 2. This is our first downsampling. The output is now 16 by 16 by 128. The height and width are cut in half, and the number of channels is doubled. And this exact pattern just repeats. Stage 3 goes to 8 by 8 by 256. Stage 4 goes to 4 by 4 by 512. At the end, we just average it all out, and a final layer maps everything down to our 10 possible answers.
This pattern is the key architectural trade-off you see in pretty much all modern convolutional networks. We are literally trading spatial information, the height and width, for feature complexity, or the number of channels. As the network gets deeper, it starts to care less about exactly where a feature is in the image, and a lot more about what complex combinations of features are present. So having the size reduces the where, and doubling the channels increases the what. Okay, so we've seen the logic, we've seen the flow, we started with one tiny block, we stacked it up, and we've traced the data. Now, let's just take a moment to really appreciate the incredible scale of the model we've just conceptually built. That's the number. Over 11 million. 11 million tunable knobs and dials, the weights and biases, that the network can adjust during training. It is a staggering amount of complexity, and was all born from that one simple, repeating residual block. That's the power of modular design. And if we break that number down, you can see the overwhelming majority of those parameters are trainable. Those are the weights inside the convolutions that the network learns through backpropagation. And that tiny little sliver of non-trainable ones, all 9,600 of them, well, those come from the batch normalization layers. They just keep track of stats about the data. They aren't learned in quite the same way. So what is the big takeaway here? ResNet-18 proved that to solve a really complex problem, you don't always need an equally complex solution. All of its power comes from one simple, elegant idea, the shortcut, just repeated over and over again. This modular approach didn't just win a bunch of competitions, it fundamentally changed how we think about building deep networks. It's a philosophy that's still at the core of AI today. It shows that incredible complexity can emerge from beautiful simplicity. So the question that leaves us with is, what complex system will you build from simple blocks?